Okay, thank you very much for being here. So first of all, we'd like to thank the Conference Rising organization, or the organizing committee for organizing such an incredible event.
Hold it much closer.
Sorry, yeah. And for having us today as well. I also would like to thank the Intern Group for the financial support, which will talk about my position now. So my name is Shvets. I'm a teacher at FabLab by Indian Affairs, and together with my collaborators, some of the collaborators online today, who works as a developer at French IT company, we'd like to share our experience on building conditional spiking adversarial neural network, along with its integration to as a core element to the adaptive VR testing using Harmony. So let's start with our slides. Yeah, so the pandemic revealed the urgent need for interactive engagement learning strategies in view of the lack of practice and immersion in the video conference format of courses. A possible answer to that problem may consist in using VR space with their solutions for content dynamization, favoring renewed practice activities and experiences, and instructions of proposed virtual activities. However, the VR devices, memory, and power limitation, along with the current AI model latency, limits the usage of AI in the VR environment. On the other hand, the development of neuromorphic sensors, together with sustainable edge computing, significantly reduces both limited factors, opening the way for on-device AI models deployment and inference. There are also evidence of future integration of event cameras to the next generation of VR devices. And if you'd like to learn more about it, I invite you to my tutorial session that will be today at 6 p.m. London time for those who are connected. Like to connect Harbour time. You may use the link, the general link if you're connected right now, so it's not a special link. Okay, so. Along with the advantages, the silicon retina, silicon ear, and machine olfaction proposes. So these are names also for those sensors, dynamic vision sensor, audio sensor, and camera sensors. A main challenge coming from these neuromorphic devices is the time distributed output data. So the time distributed data requires a specific a type of neural network for processing, which is spiked neural networks. There are several methods to overcome this challenge, which are conversion of trained artificial network spiking networks, designing and training spiking networks in the spiking domain on conventional content platforms like GPU or TPU, training spiking networks on neuromorphic remote clusters, and training spiking network directly on low power and neuromorphic chips. In present tutorial, we explored the second strategy, designing and training a convolutional spiking GAN with further integration of its functionality into an adaptive test. The adaptive test ensures the content variability for practical exercises on ear training being integrated as a module into a VR application graphs in music hall. So the interactive, the interface of the adaptive test as well as of the interactive VR application is based on the special system of knowledge presentation. This formalism allows creation of creation of mobile and web application that showed a great positive impact in the pedagogical experience that we conducted so far. So here it is. The system of graphs is based on the notions of framing graph, formulated in works by non-American cognitive and computer scientist of the 20th century, Marvin Minsky, who also happens to be the co-founder of the AI lab at MIT. According to Minsky, the frame is intended to represent this stereotyped information structure, which can be filled with different content. In music harmony, such stereotyped situation or information structure corresponds to the passing progressions, where the sequence length is always equal to 3 chords, The first and the last chords have 4 tones, so these are seventh chords. The middle chord has 3 tones. These are triads, and there will be always 3 triads possible between 2 tones chords. So graphical composition of the frame is called graph. If we feel the frame structure with all possible progressions, we see that the horizontal alignment occurs in the similar information in the top level graph, and the vertical alignment occurs in the same information according to the same information in the versus of the graphs. And if we the whole system graph comprises the chords of 7 degrees of the diatonic scale, and it's finite, meaning that if we try to build it furthermore in the somewhere in the end, sorry, we just will repeat again the information that is already present in the system. So the last element of the formalism is the color and color shades mapping, where the color is mapped to new functions and color shade is mapped to the chord structure. So now I pass the word to my colleague.
Okay, can you hear me?
Yep.
Okay, hello everyone, and thank you for having us. So, about the VR project context, the VR app runs on the Oculus Quest VR headset, which is currently called the MetaQuest. It's created using Blender and Unity 3D, which is a free 3D engine. The app itself consists of multiple virtual spaces, an entry space, a knowledge space used to explain the methodology, a study space used to explore chords and sequences, then 3 more spaces for exploring sequence generation with AI. This includes the new adaptive test module. Next, please. This is how the adaptive test scenario works. The user needs to recognize a pool of chords learned in a lesson by ear. Therefore, a sequence of 5 chords is generated with a 3rd chord hidden by a question mark. The user selects the hidden chord from the graph, and if the answer is correct, a new sequence is generated containing the next chord from the pool. If the answer is incorrect, a new sequence is generated using the same chord in question. The VR app needs to be online to connect a server to use the model, but in case the connection fails or a model fails to generate a sequence, a harmonic sequence is taken from an offline selection to ensure smooth user experience with no interruptions. So here's a demo of how the adaptive test functionality works, which illustrate the correct choice pattern. Play, please. So in this case, the user chose the correct answer and the sequence is displayed. And here's another example. Okay, next one, please. So along with adding a new module, we've also added a new functionality which allows interaction with individual tones of each chord in a sequence. Please hit play. So this way we can use the Oculus controller And actually the controller vibrates whenever we interact with the tone. So we get some feel on the interaction. Okay, next. So we've also made several optimizations to enhance the frame per second and time, the frame per second time and the fluidity of the user experience. The visibility of the frame objects and the scaling on the spaces were also reworked. Next, please.
Okay, so from this part, it's me who's present again. So this stream graph was used not only for the interface, but it was also adapted for the encoding of the training data we passed to the AI model. So this is how it works. So this illustrates the principle of data conversion. Every chord with a harmonic sequence being represented with a system of graphs receives its x and y coordinates, which allows transforming it to two-dimensional matrix. So here we have our sequence, right? So being represented graphically, we can receive the x and y coordinates and represent it with some numbers. So with the dimensionality of the of our vocabulary in the course we have. Okay, so. A new coding method allowed application of the artificial data augmentation technique consistent in invariant normalization term application. We therefore were able to present the same chord metric values in 10 slightly different variations. So basically, here is the normalization formula, right? And we are just adding a little scalar between 001 and 01, which doesn't change the value of the chord itself, but it adds some variation. And in that case, we were able to augment the dataset times 10. So the same chords, right? In normalization, 10 times, each simply represented by 10 matrices. So this, if we wanted to visualize to what our matrices would look like, these are 10 harmonic sequences visualized as 10 matrices. So this is a sequence, etc. So in order to measure the relevance of the data dimensional augmentation as well as data augmentation itself, we conducted the experiments where the 1D version of data was tested with the LSTM, long short-term memory network, and the 2D version with convolutional STM. This was done using k-false validation methodology with a k-value equal to 10, meaning that we trained 10 models per category on 10 different training validation splits of data. The training result, which is a mean value across 10 models for each category, shows that the model trained on one-dimensional data overfits. Why is that? Because we started with a validation lower, loss lower than in the study, which is not good. So even in the training loss diminishes, this difference between training validation will actually tell us that it overfits, which is actually not the case for the convolutional STM. So for the data, two-dimensional data, where we started with quite big loss of population at the beginning, and we managed to lower it down. And then when we add the augmentation of data, so 10 times augmented data, we even get better results. Let's see. The value. Yeah. So here we see that we started with the much smaller values in the beginning of training, right? For the validation split, and we diminished it to the end. So that actually indicates that our model is able to generalize much better with the small amount of data we had. Okay, so we trained the model on 2000 harmonic sequences encoded as a single matrix with the application of data augmentation technique, as we showed earlier. And here we can see the model architecture along with the hyperparameters used for training. The class of the sequence to generate was defined by the third coordinate sequence, which was like a question mark, right? In the adaptive test we were asking to recognize by ear. Since this was possible because all those data set sequences were crafted manually. So the sequence always contained the first part this passing progression that we saw in the system graphs, right? And two arbitrary chords that within the sequence. And so the model was given those three first chords, and it had to generate the true meaning. And the inference time sequence, we're going to the sequence, and we'll generate the remaining words. What conclusions we can have from this presentation is that the encoding based on the system graphs allows 1D interpretation of the same data, which makes it possible to investigate neural network training efficiency from the employment of perspective. And actually, this works for the standard INNs and spiking networks as well, so for both types of neural networks. Semantic data dimensionality augmentation allows application of architectures, evaluation, validation strategy inherent to the visual domain. So as I showed you the visualization of the matrices, right? This was possible. I can even visualize the internal state of the neurons using this methodology because it's right. It's visual. It's two-dimensional. It's coordinates that. It has been shown that dimensionality augmentation improves the generalization capabilities in the model, especially when data augmentation technique, which was possible only with this visual interpretation. I mean, with this dimensional augmentation was applied. In this paper, we also present the first conditional spiking GAN in semantic mixed generation way. Its integration to the VR learning application, which is a step forward in using spiking neural networks for building AI edge applications, so on-device inference applications, and presenting functionality possibilities of the adaptive test in music learning, open the way in development of autonomous learning systems in general and in music theory in particular. So that's what it is for us. Do you have questions?
Because of my ignorance, I was a little bit lost. But I want to ask you, so what was your first data set that you had that you then put that into the neural network? Yeah. So I'm just thinking about how it could be applied for virtual games, because we were talking a bit about that. Great.
It's well, actually, it's more. Oh, sorry.
Sorry.
Well, actually, it's more for music generation. Because for music generation. So if you want to, like you said, right, to well, we were interested in the conditional music generation because it's learning context, right? We can't generate anything. We just need to generate a specific data, right? So for that, we took the well, I actually wrote those sequences, right? Those 200 sequences, like progression of 5 words, right? And then I encoded it using this, transformation to the system. So I received the matrices, 28 to 128, and those matrices were dimensional to 28 rows on 28 columns, and that is the visual information I could take.
Okay, so sorry. So I'm just trying to formulate my question. So then you just played something, and then somebody would play something that wouldn't be quite right. There would be an error. Is that what you were doing?
No, then
I'm trying to understand.
So, and then in the adaptive test, because we have this learning application, right? So this learning application, the user can learn the sequence, etc. But then your teacher recommend the user. So for that test, for that we have actually several things that this last one adaptive test, it generates the sequence of 5 words, right? This third one is hidden. So you need to recognize the ear. What do you hear? What word do you hear? Right from the system words.
So the
user needs to put it on the graph. On the graph, he needs to choose the right word. And if the right word is has been chosen, right? So it reveals the sequence and it generates the next the new sequence with the next word to recognize the first that needs to be recognized in the and if the answer was not correct, it generates a different sequence but with the same word.
So given that, I suppose my question is, how could your work now be adapted for a user in a gaming world, in terms of maybe walking down a pathway and a music being generated, a particular sequence of music being generated, and then if they stray off the pathway, maybe the music, something indicates for them to go back on the pathway, so they're like following a musical journey. Would that be possible?
Yeah.
Just thinking how we could use that.
Yeah, well, totally, yes, but you need to train your own model that will trigger, let's say, because it's very strict framework, right? But basically, there is conditional music generation. You can, for example, condition on the emotions. So you have the progression that says that emotion, sad emotion, happy emotion, or some other emotion, and then when the user your application it should meet, like, I don't know, if you pass your data for the model or device, that you need to generate I don't know, a boring music. Understand that it should read the space, or now it's in right space, you need to generate happy music, So the model is also different by the concept is here. You are sending data to your model on the remote server, and your model generating the sequences or the music in general that corresponds to that particular trigger that you want to use in the mood or some other aspect.